clay tablets bearing mathematical problems have been found in ancient Mesopotamia dating back to 1800 BC. These include what is perhaps the world's earliest known math book, a clay slab with what we now call Pythagorean triples written on it. And there are also lots of other pieces of mathematical writing that date back thousands of years. But they don't contain numbers like we use today. Instead, they use a system of units based around whatever is at hand, usually some kind of physical object. This isn't surprising, because even in relatively recent history, people didn't always have access to paper money. They used things like cowrie shells or beads or even poker chips as currency. In fact, people still use this method in some places today. For example, in Papua New Guinea, people use something called a vote as currency. A vote is a token that is typically made out of a plastic disc and can be exchanged for goods and services. So writing down quantities in terms of physical objects makes sense, but how do you write down quantities of things that aren't physical objects, like time or angles or area? Well, sometimes they use a clever trick. Like to represent time, they could say a certain number of barleycorns squared. You might think this is a strange way to measure time, and it is. But just like today, different units of measurement were used for different purposes. So it's not as weird as it seems if they used area to measure time. That is, after all, what we do when we talk about a time squared or time cubed. But there's another even weirder unit for time that pops up in some clay tablets, and that is the unit of 1/60th of a degree. If you've watched my video on angle measurement, then you'll know that a circle has 360 degrees in it, which means that 1/60th of a degree is equal to 6 minutes, and that's exactly what it is being used for here. Take a look at this tablet. It looks pretty abstract, but let me orient it so it makes more sense. The horizontal axis represents an angle from 0 to 360 degrees, and the vertical axis, well, let's find out by counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this is a sexagesimal system, which uses base 60 instead of base 10. So each tick mark is worth 12 degrees. So the vertical axis goes from 0 to 360 degrees. If we follow the horizontal line to the right, and then go up to where it intersects the vertical line, we find ourselves at this point over here. Now, there's no neat way to say this without using trigonometry, but this angle is equal to 19 degrees, 20 arc minutes. Arc minutes, by the way, are just another name for degrees. In this case, 20 arc minutes. Okay, so we start at 0 degrees, move along to 19 degrees, 20 arc minutes, and then move upwards to 1/60th of a degree. There's only one way to do this. We can take a step of size 1/60th of a degree in exactly one direction. That's to the north. This means that if we subtract 1/60th of a degree from our angle, we end up at 19 degrees, 19 arc minutes, 59 arc seconds. I'm sorry, there's no real neat way to do this. It's just a little bit of trigonometry. Now, looking at our tablet again, we can see that every single one of these points follows this pattern. If we take 1/60th of a degree off our angle, we land on the next point on the list. What this means is that this whole thing can be expressed as a simple formula. Let's use n to represent the number of degrees on the horizontal axis. Then the number on the vertical axis is given by 19 degrees plus n arc minutes minus 1/60th of a degree. Here's a more explicit version of the same formula. If we take the horizontal axis to be the number n, then we can write the vertical axis as 19 degrees, 20 arc minutes minus 1/60th of a degree plus n arc minutes. We can combine these arc minutes into a single term, which gives us this nice little formula. This formula lets us calculate the vertical axis for any value of the horizontal axis. But conversely, it also means that we can solve for the horizontal axis, giving us this formula. These two formulas may look complicated, but they're not really, They're just algebra. And this is what makes it so amazing. All those thousands of years ago, someone was doing high school algebra. But what were they actually using this for? Well, unfortunately, we don't know. But it probably had something to do with astronomy, because a lot of clay tablets contain astronomical data. But that doesn't mean that they weren't using this kind of math for other things too. Maybe they had a clock that looked a bit like this. You see, to tell the time with this clock, you would first need to know the hour angle of the sun. The hour angle is the angle between the sun and the observer, projected onto the celestial equator. This is measured from the perspective of the sun, which is why it starts at 0 degrees at sunrise and reaches 360 degrees at sunset. If you want to know what time it is, you can use the angle of the sun above the horizon and its hour angle to work out the time. But you need to know the hour angle of the sun relative to your location on Earth. And to do that, you would need to know the coordinates of your location. For example, if you're in Edinburgh, then you need to subtract 4 degrees from the sun's hour angle. This is because Edinburgh is 4 degrees west of the prime meridian. Similarly, if you were in Samarkand, you'd need to add 65 degrees to the sun's hour angle, because it's 65 degrees east of the prime meridian. This is all pretty complicated, but maybe they had a clock to help them. And maybe this is what they were using this kind of math for. I don't know. All of this speculation is fun, but we can turn it into something a bit more concrete. The formulae we derived earlier can be used to calculate the horizontal and vertical coordinates of every single point on this circle. If we put the origin at the center of the circle and the radius to be 1, we get the following parametric equations. This is a great example of how mathematics is interconnected. Here we're using ideas from trigonometry and algebra to describe geometry. And we can plot these parametric equations to reproduce our original table. The coolest part, though, is that these parametric equations can be solved for x and y to give us Cartesian coordinates. If we substitute the second equation into the first and use some trigonometric identities, we get this. This is the equation of a circle. And if we take the equation of a circle and shift it around, rotate it, scale it, and move it in and out of the plane, then we can get all kinds of different shapes. This is the basis of computer graphics, and this is why I love math. It's everywhere. Now, I haven't been able to find much evidence that ancient Mesopotamians knew about parametric equations or computer graphics. But I did find this tablet, which has a drawing of a bow and arrow. And it got me thinking, could they have used these coordinate systems to solve projectile motion problems, like calculating the trajectory of an arrow? After all, this is the basic principle behind a compound bow. The more you pull the string back, the higher the arrow will fly. But to actually calculate the trajectory, you would need to know the angle of elevation, the initial velocity of the arrow, the acceleration due to gravity, and the height of the bow, among other things. This would have been quite challenging without the aid of mathematics. So I started plugging some values into our formula just to see what happens. And lo and behold, we can reproduce projectile motion. I'm not saying that this is what they were doing, but it's certainly possible. And if they were using this kind of mathematics for archery, then that would explain why there's so many drawings of bows on clay tablets. Of course, this is just speculation, but this is what's so great about mathematics. It connects everything together. You never know where a piece of research will end up taking you. Thanks for watching. I hope you enjoyed this episode. If you did, don't forget to subscribe and check out the website below for more information and interactive visualizations. Special thanks to my patrons and donors for making these videos possible.